Let's suppose for a minute that TCP flows from all 20,000 senders are synchronized. And for a single sender, you'd see a sawtooth between Wmax and Wmax over 2, and every other sender would have roughly the same characteristic. Now, when you sum these up, the aggregate window, of course, would have the same basic dynamics. Therefore, the buffer occupancy would have the same dynamics, and the only difference are these quantities, but the rule of thumb would still hold. Now, a small number of flows may be synchronized, but it turns out that as you increase the number of flows, this type of synchronization disappears. And in fact, measurements in the core of the internet give no indication that TCP senders going through a router experience this type of synchronization. Instead, what you might see is some flows sending with slightly desynchronized or different dynamics. Now, if these flows down here are not synchronized, what you'll see up here is not a clean, large sawtooth, but instead something that looks more all over the place. And now the buffer size no longer needs to be the height of this sawtooth, but instead we might be able to get away with a much smaller buffer. Now the trick is that this orange line representing the aggregate traffic of all the senders is no longer a nice clean sawtooth, but in fact it's a random process representing the sum of a bunch of random variables, each representing the window size of a TCP sender at any given time. And what we want to do is figure out what the distribution of the resulting random variable representing the sum of all these senders' windows is. Fortunately, we know how to do that. We can represent this quantity as a Gaussian. And the central limit theorem tells us what the distribution of this variable is likely to be. Now, if we basically take the height of this orange line at any time to represent our random variable, we can represent the height of that line, which is effectively our required buffering, as a Gaussian. And the central limit theorem says that the width of this Gaussian distribution is proportional to 1 over the square root of n. So as it turns out, the required buffering is actually not 2t times c, but actually 2t times c divided by the square root of n. So in summary, flows in the core of the network may not be perfectly synchronized, and therefore we can represent the required amount of buffering as a random variable, which is simply the sum of each of the TCP sender's windows, each of which is a random variable. This gives us a Gaussian whose width is proportional to 1 over square root of n, and therefore the required buffering is also inversely proportional to square root of n, where n is the number of active flows. Now, in this example, we've essentially assumed a congested router with long flows in the steady state congestion avoidance mode. Now, what about flows in slow start or shorter flows? The buffer requirements, of course, differ in these cases, but the required buffer in these cases is still independent of the line speed. It's the same regardless of whether the line speed is 1 megabit per second or 40 gigabits per second. So in mixes of short and long flows, the long flows still drive the buffer requirements. And buffer requirements for short flows are really only relevant if the router is uncongested.